Okay, and we switch to the next speaker, and I welcome Radim Filip from Polaki University Olomouc, Czech Republic, right? Is it correct pronunciation?
Yes, Czech Republic, exactly. Do you hear me well, everybody? Do you hear me?
Yes.
Yeah, very good. I would like to thank organizers because organization of such a workshop under all these circumstances, this is a big deal. And I'm happy to participate, and there were already quite interesting talks and quite interesting talks as well follow after my. Which means I would like to contribute, as I was asked as well, by the overview of the activities which we are doing at our Department of Optics in Olomouc at Polack University. Of course, I would not be able to go through all the activities because there are 80 researchers working very actively. It means this is not overview over all department, but just overview over the team which is around me. The team is, the team, as you could see, is already quite big. There are many directions. Actually, there are not all photos of members of the team because it was not possible to actually make it at the one slide. But I would like to just go through the titles of the different directions which we are doing, and then you will see more details and results in the following slides. Like recently, the most active topic are quantum non-Gaussian states of light and matter. These are the states which are not anymore any mixture of Gaussian states. It means they have features which are more exotic than just normal squeeze states and all of their convex combinations. And we very much study these states. We try to find the new ones, develop methods for their preparation and detection for both light, but as well for mechanical oscillators, for atomic systems, and for conducting circuits. Then we try to use these states to perform operations with light. This is quite challenging theoretical research, but is as well much more challenging experimentally because we want to do these operations deterministically. The third section is basically focused on quantum communication. And there we do quantum key distribution with continuous variables, but as well we started to do this more and more with non-Gaussian states of light. The other section uses all the knowledge which we accumulated in quantum optics and tries to plug that knowledge to the optomechanical systems. It means we try to more integrate quantum optics with the recently attractive mechanical systems. And you will as well hear a bit about that. Then we, in 2015, quite deeply dived to matter systems like atoms and trapped ions, because we were able to finance through our Center of Excellence new laboratories, which are in Olomouc and as well in Brno. And these laboratories are now looking together with us to the new experiments, both with the light emission from the atoms and ions, but as well to experiments where we control non-classical states of mechanics of these systems. And we use this as well for quite sensing applications and applications in quantum state estimation. Then two actually newest subjects are connected to the systems which are very modern, modern quantum solid state systems where we search for autonomous quantum coherencies. And I think the biggest hit of last decade, and these are superconducting circuits, which really took over traditional quantum optics. And they are really at the front of abilities to generate interesting quantum non-Gaussian states, as we will see. I would like to very much emphasize the role of Vladislav Usenko, who actually came from Ukraine. He was my first foreign postdoc. It was more than 10 years ago. And with him, we started to collaborate on quantum key distribution, and this is what we do still until these days with big success. And he already involved other people from Ukraine, like Ivan Derkach, Olena Kovalenko, and as well Maria Gumberidze, which is now switching actually from one subfield to another. Okay, we have these experimental facilities which were developed over last 10, 15 years. And these are mainly traditional quantum optics experiments with photons, then experiments with trapped calcium ions, where we both study emission of light, non-classical emission of light, and as well preparation of interesting non-classical and non-Gaussian states of mechanics. And then experiments, with hot rubidium atoms in the cell, where we actually try to not only generate the states, but as well try to store the states, quantum non-Gaussian and non-classical states of light inside the atomic memory. Of course, we are more theorists than experimentalists in my team. Therefore, we use a lot of experimental collaboration with other teams in Europe, but as well in the whole world. You will see some experimental results from Erlangen, as well as some collaboration with Danish Technical University, something what we do together with Akira Furusawa at the University of Tokyo, something as well from Paris, from group of Julien Laurent and Nicolas Traps. And you will as well hear about collaboration with Markus Spellmayer and Steve Girvin, first at Vienna University and the second one at the Yale University in the US. Okay, this quantum non-Gaussian world, this is actually the world which is almost entirely undiscovered. What Marco showed was beautiful first steps which optics could do to enter the world, to operate systems and quantum states at a low photon level, very individually, to reach very basic non-Gaussian states like Fock states, their superpositions. It means the non-Gaussian world is actually quite rich, and we are somewhere maybe around here, where we operate these Fock state superpositions with light up to maybe 3 photons, as I will show. Then with mechanical motion of trapped ions, we could go a bit farther. I will as well show you a bit. And then with superconducting circuits, we can get somehow comparable numbers of the Fock state superpositions for microwave fields. The globe, of course, has another pole. This is pole of even more exotic states, which are very non-Gaussian. They are non-Gaussian because these coefficients here of the superposition in the position bases, they have exponents which are modulated by the position dependency with power larger than 2. And these states are very hard to build by the finite methods of the superposition of the Fock states. You need to develop something much more exotic. Ideally, you need, for example, the motion of a nanoparticle or atom in some very exotic nonlinear potential, which is fully covered by quantum rules, which feels very small decoherence. It means you see that the track from here to there is still in front of us, and there are plenty of the chances for all the people to discover new continents in this quantum non-Gaussian world. There are already known applications of these quantum non-Gaussian states. They were experimentally tested, for example, for sensing the use of the Fock states and on states, it means superposition of 0 and n quanta. For error correction, there is a big deal with all binomial codes, but as well JKP codes and all error correction methods for bosonic systems, which are quite reasonable candidates for error correction, quantum error correction for the future quantum computers. There are as well considerations to use these states for quantum communication, quantum simulations, even quantum thermodynamics, and maybe many other applications of quantum non-Gaussian states will come, because there are more and more people interested in quantum nonlinearities and quantum non-Gaussian states in general. First, maybe a bit of what is the basic of these quantum non-Gaussian states. This is the research which basically I started more or less 20 years ago when I finished my PhD. It was very, at the beginning, very theoretical. There were more or less no experiments at that time with non-Gaussian states, except the experiments with a few experiments with trapped ions and and superconducting cavities in Paris. But gradually they were developed, and we started to look more and more to the serious problems with these states. And I would like to emphasize the role of Lukáš Lachman, who is actually fresh postdoc in my team, and who is basically taking care about majority of theoretical research in that direction together with me. These quantum non-Gaussian states, if you do the first very simple comparison for the simplest example of them, it means for single photon state of light, they behave already very differently. Their formal definition is that these are the states which are incompatible with any convex mixture of all possible Gaussian states. And of course, as was mentioned in the previous talk, negativity of the Wigner discussion, negativity of the Wigner function is one of the possible witness of such a state. But as we all know, this is very sensitive to loss. And if you have loss more than 50%, then we can't see negativity of the Wigner function. It means it was for a long time a question in quantum optics, quite a practical question, whether we can see anything out of the non-Gaussian states behind the limit of 50% of loss, which was very tricky limit for majority of the experiments, especially new experiments from solid state physics when the losses are large, as well experiments with the free emission of the atoms or ions, they as well suffer from quite large loss. Means we look first to that specific corner, and after some attempts, we found a way how to actually build criteria which are much more robust than against the loss than is the limit of the 50%. We found them, they are in the simplest form written here, where you think about just very simple HBT measurement to detect quality of the single photon. It means the same measurement which is used for the test of non-classicality for the measurement of G2 correlation function. And then you just evaluate coincidences. It means probability of the multi-photon clicks versus the probability of single photon clicks. And you have some inequality, and if basically you fulfill that inequality, you know that state has these quantum non-Gaussian features. It means it's incompatible with the mixture of all possible Gaussian states. It's interesting to compare this criterion with the criterion which is above, which is standard non-classicality criterion. You see that it looks very similar. There is different prefactor, but the main difference is actually in the power of single photon probability. That changes from the power 2 to the power 3. And that makes basically this quantum non-Gaussianity in principle sensitive to the loss, but the advantage of this criteria is that it can be very tolerant. It means it can survive losses around 20 dB if your single photon state is of reasonable quality. And this is what we already saw in the first experiment, which was done more than 10 years ago. And we saw that we could really generate states, single photon states, which are very attenuated, but they are as well very far away from the threshold of all possible Gaussian states, which is here denoted by the blue color. Since that, there were many, many experimental tests with solid state systems, with individual atoms, with atomic ensembles. It means that criteria were quite applied to many different experimental platforms. But later we were very interested whether we could advance this criteria to the multi-photon state, whether we can somehow recognize that we are approaching maybe genuine features of higher Fock states than just Fock state 1, which is the ideal form of single photon state. That took quite a while, few steps towards that, and as well, there were some experimental tests during that progress. But at the end, we were able to formulate quite nicely approximative criteria, which are working very well for these very dim, very low efficiency kind of sources, which are typical for many new experimental platforms. And then we could test this criteria on our quantum optics experiment. But then we realized quite important feature, that our parametric down conversion experiments, where we use basically trigger in the form of single photon detector with already quite high efficiency, because these are all superconducting detectors, that even these detectors, if we use them as a trigger, they are not able to trigger better quantum non-Gaussian states than these which corresponds to Fock state 3. It means we can't go right now with optics farther. We need better sources to break this limit. And this was as well one of the motivation why we entered to the fields with other systems, like with atoms and their mechanical motion, and as well to the field of superconducting circuits. We developed as well other types of criteria because we felt these limitation quite substantially. We thought maybe we should try to access the single photon and two photon states, which are quite accessible in these days from the different perspective. And we indeed did that using so-called multi-copy criteria. Means these criteria, they combine information from many totally independent copies, totally independent repetitions of the experiment. And they basically ask how this collection of states about which we maybe naively could think that they are very similar, how indeed that collection of the states could work in linear optical network and what could actually happen there. And one interesting aspect is that maybe with low probability, but still non-zero probability, for example, n more or less ideal single photon states could merge in the linear optical network to Fock state n. It means we can test like whether that sort of rare event, but very extreme event, actually could have a features which we expect. It means features of the Fock state n, namely, for example, the adequate number of the negativities of the Wigner function. We looked to that problem first theoretically with Petr Zapletal, and then we were very interested in how that will look experimentally. And we collaborated with Julien Laurent in Paris, and they did quite many measurements, independent measurements of their single photon state, and then we work on the data processing. And at the end, we realized that actually this dependency, which we found in the theory as very nonlinear, is indeed observable in experiment. And the main aspect of the nonlinear dependency between quality of the single photon state and its Fock state capability is that there is sort of like threshold in single photon efficiency. You can see it roughly here. You know the number of the threshold very exactly. And after that, you could more or less generate any Fock states. It means if you have adequate number of the single photon state that you will, and single photon state, that you will always get that Fock state n with the very nice oscillations of the Wigner function in the phase space, as is, for example, documented here for collection of 14 different single photon sources. We indeed, when we process the data, we indeed predicted that if these photons will interfere in the linear optical circuit, then they will have a capability to generate beautiful negativity of the Wigner function corresponding to that Fock state 14. What was surprising is that when we then looked to the photon number distribution, this was much more sensitive to the quality of the generated state by data processing than actually in the negativity of the Wigner function. It means this is simple take-home message. If you want to have something very sensitive for the evaluation of quantum non-Gaussian states, like Fock states, for example, it's better to use photon number distribution for the evaluation than the Wigner function. That was quite surprising. These states, they are not only of interest for their fundamental features, they are as well, as Marco showed, the useful resources to play various types of interesting games and applications with quantum states of light. Namely, they are very good resources to power the operations. In the Marco's case, majority of these operations were conditional. They are still very interesting, like nonlinear, noiseless amplification. But we focus more on operations with team of Akira Furusawa, which are deterministic. We started by a very simple deterministic operation on the single photon state, which was just squeezing and amplification together. Here you can see the noise track corresponding to many repetitions of the single photon experiment and the oscilloscope. And here you basically see how we can squeeze in the phase dependent way these noise tracks for the single photon and we can amplify them for the phase which is orthogonal, and then we can do it even more. And at some point, we basically build something like cat state deterministically out of the single photon state. Here you see basically the results of the interference. It means very bright component, which is coming actually from the constructive interference. But these are all still linear operations, and we paid a lot of attention to develop the tools and circuits for nonlinear operations, which are extending what I showed just experimentally before. There are not yet any of these experiments fully running, but we already built and tested the pieces of them. Namely, we tested this kind of nonlinear measurement with special nonlinear electro-optical feedforward. This is already running. And our recent latest contribution was actually to prepare this very special state, which is called cubic phase state. It ideally has very interesting shape in the Wigner function, very unusual. It doesn't look like Fock state or cat state. And that shape is actually used to compensate noise in that circuit and to reach nonlinearity, which is cubic, online on the traveling beam of light. What we could do, we could approximate these states. If we use superposition up to 4 photons, that it will look like this. You see that this is only a fraction of it. If you use superposition of 0 and 1, then you see that this is indeed a very different state. But that amount of noise suppression, which we call nonlinear squeezing in that state, is actually something what we really want to observe. And even in that state, I could show you the experimental data in the superposition of 0 and 1. That amount is non-negligible. The result of experiment is here. It took quite a development in theory as well in the experiment. But at the end, we were able to see minus 0.05 of so-called nonlinear squeezing. And this nonlinear squeezing is noise suppression in nonlinear variables. It's nonlinear variable y, which is you see combination of the momentum with x squared. And this is actually what you need to compensate the noise in the circuit and obtain the nonlinear cubic phase gate, which is important thing for quantum computing with optical traveling beams of light. Yes, I think I will just now go quickly through all the rest of the subjects. In quantum communication, together with Vladislav Usenko, we have a long history in the CVQKD, in the quantum key distribution with continuous variables. Recently, we paid very much attention to the multiplexing of the CVQKD using basically frequency comps. I mean, this is similar a little bit to what as well Marco is using. It's a pulse system. And here there is a great progress. We could basically increase the secure key rate once we obtain it by using these frequency modes. The problem is that typically these sources, they suffer from the crosstalk between these modes. And then together with Olena Kovalenko, we were able to devise the method, which was able basically after the measurement using the homodyne detection on the Alice and Bob side to somehow improve and these measured data and eliminate that crosstalk from them. And that was very nice progress. You see, without the elimination, there was barely visible secure key rate, which didn't increase with the number of the pairs, entangled pairs at the different frequencies. But once we apply these crosstalk cancellation, we actually got quite steep increase of the secure key rate. It means it's really paid off, and it's simple data processing, which we have to do in addition to the homodyne measurements, which we use for CVQKD. There was as well big interest together with Ivan Derkac to solve problems of the side channels in the CVQKD. These are special channels which are half, only partially, only half somehow in the hands of the eavesdropper. Sometimes they are overestimated or underestimated, and that could cause a lot of problems. It means Ivan was working during his PhD on that quite a lot. And as well, the other direction which we pushed in the last years is atmospheric CVQKD with all the fading effects which we have in the free space channels. It means you can read more about this in our recent publications. The other fields, as I mentioned, are quantum optomechanics. There is a lot of work which we do together with the group of Markus Spellmeyer. We are very much motivated by the levitating experiments, which are basically optically levitating very small nanoparticles. And by cooling using the feedback or cavity, they were already pushed with the noise down to the ground state for the center of the motion. And this is opening new possibilities because we can manipulate these optical potentials inside the optical tweezers and get maybe to that other pole, to that south pole, which I mentioned at the initial slide. We already do this as well in Czech Republic. Note that the ground state still in quite noisy levitating particles, with quite noisy levitating particles, but already in the classical domain, we already saw plenty of interesting phenomena. And now we are going to more semi-classical regime, and hopefully after some experimental effort, we will reach some interesting quantum regimes. We are not 100% sure what exactly will be there. It's all very exploratory and very interesting. We expect that we could see, for example, in the shapes of the potentials, which are like cubic in position, that we could see negativities of the Wigner function, which are really appearing for a very short period of time, much shorter than are by basically recoil effects in these experiments. There are plenty of the other proposals. You see, optomechanics was a really big topic over the last years, and it will definitely continue in our team. Atoms and treptons, this is another type of experiments. As I said, we do experiments with light, but as well with mechanics. We actually try to address the mechanical motion of the treptons in such a way that we will push that motion to non-classical states. Here is one demonstration of type of experiment, which is a bit similar to the Marcos photon edition. Here it's more the phonon edition. And we try to prove that we can gradually add more and more phonons, more and more single quanta to the thermal state, and push it really towards the non-classical region and even to the non-Gaussian region, observing the negativities of the Wigner function. Then we as well tried how good actually Fock states these systems could generate. And we find out that they could generate really beautiful Fock states. We tested Fock state 10 with quite clear non-Gaussian features. As you could see here, this was the result of the experiment. And this was threshold, the most strict threshold we could find out for the non-Gaussian features, much stricter than the negativity of the Wigner function. But simultaneously, we realized as well that if we apply them to the simplest task, which is displacement sensing, to sense recoil effects, which are basically appearing when atoms emit, then these Fock states, they still do not have sufficient quality. You see, this is the green threshold, and we basically stop rather here with the quality of the Fock state for this displacement sensing. It means there is still a lot to develop, although that platform looks as the most promising one for the recent experiments with quantum non-Gaussian states. We as well applied them to the sensing. The simplest task to which you could use them is sensing of the phase randomized displacement, because then you know that actually Fock states are optimal and detection of the Fock state is optimal too. It saturates even quantum Fisher information. And we elaborated on that, how well the finite sample strategy will work and to what extent we can actually do these experiments. And now they are in a laboratory under the tests. But we as well realized some interesting things, that sometimes we could emulate the more or less same quality of the results using some clever strategy with the Gaussian states. It means not every time we really need these non-Gaussian states. If we think of Gaussian states, sometimes we could reach almost the same. It means it's all interesting to look where actually this non-Gaussianity is needed. Yeah, we as well study these special autonomous coherencies. This was quite interesting work of Maria Gumberidze. She tried to develop something like quantum coherent synthesizer to synthesize very little coherencies, which we can get autonomously from solid state platforms. It was actually stimulating our single photon optical lab, and they looked to the new types of operations which we could do on the single photons. And they did tests how well these operations can be performed. And we realized that this is actually much more demanding than the previous experiments we did with the single photon states. Superconducting circuits, yeah, we try very much to go forward to design the schemes for error correction codes, for JKP states, and then as well to have alternative ways to reach these nonlinearities, the cubic nonlinearities or quartic nonlinearities in superconducting circuits. And this is all done with the help of Steve Gerwin and others at the University of Yale. Without them, that will be much more complicated. And it was in very nice collaboration with Ulrik Andersen and his colleagues at Danish Technical University in Denmark. Yeah, this is probably where I would like to stop and just show you current state of the art of this field. It looks a bit like this. We know roughly the borders, but we don't know what at the end will be the picture, because there are still many uncovered and unexplored parts of the continent. We have very good plans what to do next, and we search for PhDs and postdocs. We have plenty of the positions available to join our research. Thank you very much, and I am looking forward to questions.
Thank you very much. We almost, not almost, but even finished already the time of the coffee break, but still, if we have questions, and especially, okay, I will read the question from Konstantin. What quantitative criterion have you used for non-classicality of photon state?
Yeah, this is very complex problem, because these non-classical states, they can be very diverse. They can be squeezed, they can be closer to single photon states, they can be closer to another very exotic states, even non-Gaussian states. They are still non-classical. It means there is not a unique criterion which we could apply. There is not unique measure. And personally, honestly, I believe that there will be never unique measure of non-classicality, because this is a very diverse work. It means we really try to adapt the criteria to the experiments which we have in mind. For example, when we have this type of experiments like single photon emission, then the lowest sort of criterion we could find is to measure second order correlation function, G2 function, and test that. However, this criterion is not very useful, for example, when we generate squeezed light, and it's not useful at all when we generate cat state. Yeah, it means we have to really adapt this. We have to have a prior knowledge what kind of states we are approaching, we are targeting, and then we can devise the criteria towards that. This is actually the approach we took. It means we are very operationally oriented. We use that prior knowledge about what we want to generate and how we measure to devise the criteria exactly for the experiment, which is in laboratory.
Okay, thank you. We can't miss the question from the next speaker, so Andrei, please.
Okay, Radim, very short question. So thank you, yeah, of course, thank you for your talk. And my question is it correct to say that non-Gaussianity can be considered as a resource for creating states which are more stable against, whose correlations are more stable against noise, such as losses, for example?
Yeah, I think you touched a very important and very beautiful point, because these error correction codes for bosonic systems, for example, the JKP states to which we paid attention here, they are indeed the codes which are used to correct against the small loss, but still the loss. It means normally we think that non-Gaussian states, they are extremely sensitive to loss, but still you can construct a so-called grid states. And they have that fantastic feature that if you apply a reasonable amount of loss to that state, then actually they change to something orthogonal, which is not only detectable, but even correctable. It means this is a quite interesting thing, which is correcting many, maybe quite blind considerations about non-Gaussian states, because when people say non-Gaussian states, many people imagine Noon state. And then they remember that null state, if there is epsilon of loss, they loses their metrological power. But there are other types of states, like for example, these JKP states, which are actually non-Gaussian very much, and they are used for as error correction for the bosonic.
Okay, thank you.
Okay, probably a very short question. Probably I missed. It was not missed. It was too fast for me about multi-channel detector, and my question is just related. My favorite technique is angle result photoemission spectroscopy, photoelectron spectroscopy. And have I understand right that it is just the way to get the angular resolution of photons?
No, here it's basically you have like a frequency comp, and you have like entangled pairs inside the frequency comp on left and right side of your comp. And now when they are generated, they actually feel the crosstalk. Yeah. But if you have in mind continuous variable key distribution and you apply homodyne detection technique, then you actually gain enough information to combine all these measurement results on dead modes to completely eliminate that crosstalk out. That means that crosstalk, after proper optimized data processing, will totally disappear. It means if I answer the question which you posed, I hope so, then this is the technique which is very useful. It's impossible, this is interesting, to do this with the single photon quantum key distribution.
Okay.
This is special power of continuous variables, of the wave nature of continuous variables that we can do that.
Okay, thank you. Thank you very much for interesting talk. I stop the